We're done. All right, today we're talking about mass spring systems in simple harmonic motion. We're now no longer just looking at a pendulum, we're looking at a spring system as well. So what is simple harmonic motion? When we say simple harmonic motion, what exactly do we mean? All right, so when we talk simple harmonic motion, we are really talking about periodic motion, number one. So periodic motion, which means it's moving repeatedly over the same path in equal intervals for time, okay? These are called oscillations, and the periodic motion is going to be directed towards an equilibrium position, okay? What that means is that as the spring is springing back and forth, or if the pendulum is rocking back and forth, it wants to go back to where it would be if you just left it alone and it went to rest. So for a pendulum, we're talking about equilibrium being at the bottom. So this will be equilibrium. And for a spring, we're talking about where it would be if it was unstretched. So if we let it just sit there, it would be at an equilibrium property. So if something is undergoing periodic simple harmonic motion, it has two simple characteristics. Number one, the force acting on the object is going to be directed towards equilibrium. Think about why that is. Because the spring or the pendulum naturally wants to go to equilibrium. So if the pendulum is rocking this way, the force is still, if the motion is that way, the force is still going to be towards equilibrium. And same with the spring. If the spring is moving away from equilibrium point, then the force is still trying to restore it back to equilibrium, all right? The force is also proportional to the distance it is from equilibrium. Okay? Proportional to the distance from equilibrium. In other words, the restoring force is which is what we're going to call it. Is going to vary. Let's write this correct English. It varies linearly. That's what proportional means. Linearly with displacement. Okay? So, why does a pendulum only approximate simple harmonic motion? So what is the restoring force for a pendulum? I'm hoping you're saying it. What's making it go back towards the bottom? Gravity. Now, unfortunately, gravity acts which way? It acts downward. Not towards equilibrium, technically. So if we've got this guy right here and we've got a pendulum, force of gravity is acting this way, but equilibrium is this way. So it's not exactly opposite, is it? So it is dependent on the force that's actually going in the direction, taking it that way, is sine theta. Okay? So only S sub g sine theta acts towards equilibrium. So it's not directly proportional to the distance from equilibrium. Okay? Now, we can still treat it like it is simple harmonic motion if the angle it makes is relatively small, which is why you'll never see in one of these questions them talking about a really big angle. It's just a very small angle towards. So that angle, we can have simple harmonic motion if theta is less than about 20 degrees. Okay? So now, what is amplitude? It is the distance. We saw this before. It is the distance from our max displacement to equilibrium. The period is, of course, time for one complete cycle. And the frequency is going to be 1 over the period. That's little f. So it is going to be cycles per second. And frequency is, so that is s to the -1 or hertz. Okay? So now, if we have a mass vibrating at the end of a spring that's undergoing simple harmonic motion, what do we know? We've got a restoring force. Okay? This is the force that causes the system to return to equilibrium. This is given by Hooke's law, and Hooke's law says F equals negative kx. Now, you may be wondering why there is this negative right here. Because, what did we say? It wants it to restore it. So, if the block is moving this direction, so if it is moving with some velocity that way, then guys, the restoring force is in the exact opposite direction of that motion. Okay? So the restoring force is going the other way. So we have this negative sign to indicate that reversal of direction. All right, so what do these stand for? K is the spring constant. That is how stiff the spring is. So the higher the spring, that number is, the stiffer the spring is. Okay? Now, X is the displacement. And that is from equilibrium. And of course, F is our restoring force. Okay? So now, what is the period of a mass spring system? What is that going to be equal to? Period of a mass spring system, I know you'll be surprised by this, but it contains 2 pi. Think about why. We're going back and forth and back and forth and back and forth. That is, periodic behavior includes 2 pi. And it usually includes, because it's almost like it's circular, isn't it? This is on your purple sheet. Okay? Now what are you going to notice? That you're going to notice that the period and mass are directly proportional. Think about it. The period is here, the mass is here, so they are directly proportional. So, in other words, as the mass goes up, the period goes up, doesn't it? And it is inversely proportional oops, didn't need to do that. Inversely proportional to K. So as the spring stiffness goes up, the period goes down. stiffer the spring is, the harder it is to get it to move anyway, right? And that didn't take, so as M goes up, T goes up. Now, what's the equation of oscillation? Well, if you think about it, it's going back and forth and back and forth, and we did tie it to circular motion. And so what we're getting is this rhythmic thing, and when we think of circular motion is we think of sine and cosine. We actually write the equation of oscillation as the position over time is equal to the amplitude times the cosine, because it starts away where it starts high, and remember cosine from pre-cal starts high, okay, equal to the angular velocity times time plus whatever phase shift there is, okay? Now, what is omega in this case? Omega in this case is equal to 2 pi over the period, okay? And the phase shift is just the initial position. If the initial position is not the same as where it normally starts, then that is the phase shift, okay? Now, there are only two types of positions with a spring. Two positions we're interested in. We are interested in equilibrium and maximum displacement. Now, I hope you're seeing that this looks an awful lot like the pendulum, doesn't it? Sure does. So, what do we notice? What do we notice is that we know equilibrium will be right here at rest. So we have now pulled the spring away from equilibrium at time 0. That means its displacement is at a maximum to the right. Now, when we pull it to the right, we're holding it, right? So the velocity is 0, which means the kinetic energy, of course, is 0. You see the relationship this has? It's the same as what we saw with the pendulum, isn't it? Now, if this thing velocity is coming to 0 to the right, that means the acceleration must be at a max, but to the left. If it is at a max to the left, then the force must also be at a max to the left. Now, if displacement is at a max, then we know the spring kinetic energy, or the spring potential energy, which is 1/2 kx squared, if you remember, is also going to be at a max. Now, this thing is now moving, and let's take it phase by phase. This thing has now moved this way, and it is at equilibrium. So if its position is at equilibrium, it is now going at its fastest. So this is at a max. In which direction is it going? It's going to the left. If it is at a maximum velocity, this is where it's going to be going from a max, and now it's going its fastest, so now it's going to begin slowing down as it goes the other direction. If it's slowing down, that means the acceleration is switching directions, which means the acceleration must be 0. If the acceleration is 0, that means the force is 0. Okay? If this is at equilibrium, which of course is at x equals 0, then we know our potential energy, spring potential energy, is at 0. But we also know that the velocity is at a maximum. Kinetic energy, which you remember is 1/2 mv squared. Velocity is at a max, then the kinetic energy is at a maximum. Now, we have now moved back to equilibrium. I'm sorry, past equilibrium. We have now moved this way past equilibrium, haven't we? Let's do this in a different color. We've now moved past equilibrium that way, and we have come to a stop. So this is at max displacement, only this time it is to the left, which means our acceleration must be a max. Only this time, what is it? If it was max to right, it meant it was accelerating to the left, and if it's max to the left, it must be accelerating to the right, correct? The velocity, it's slowed down now. If the acceleration is at a maximum, it means that this thing has come to a stop, which means our velocity is 0. So our kinetic energy is 0. If our acceleration is a max, that means these go together. That means our force is a max. And if this position is at a max, then our spring potential energy is also at a max. Now, what happens next? Now we know this thing has now moved from equilibrium. It is now moving, or from max displacement, it's back towards equilibrium, which means this is now at equilibrium. It's back at x equals 0 again. That means its velocity is at a max, only this time it's moving to the right, which means that its force is a max, but it is to the opposite direction, is to the left. Oops, I put that in the, did I put that in the right place? No, I didn't put this in the right place, excuse me. The velocity is at a max to the right, which means the kinetic energy is at a max. What was I thinking? All right, if this is at equilibrium, that means our spring potential energy is 0, because it's 0. Now, acceleration. If we are at a maximum velocity, it means our acceleration is 0, which means our force is 0. At equilibrium, it is not trying to restore itself to equilibrium, because it's at equilibrium. Makes sense if you think about it. Okay, so now finally, we go to the last phase, which is we are now moving off equilibrium and back to the right again. So now we are at a max to the right, and this should look exactly like the last one. Velocity 0, because we've come to a stop. Acceleration is max, only this time it's opposite the positional, so it's to the left, which means the force is a max to the left. Kinetic energy is off of position, so it is at a max, and potential energy is off position, so it is at a max. Okay? Oops, what did I do? Which one of these is wrong? Excuse me. If velocity is 0, then this has to be 0 too, doesn't it? These two at max. So we've done one full cycle here. We've gone from one to the other. This is one cycle, which is equal to 1 period. Okay? One cycle is equal to 1 period. So now let's look at some examples. Okay? So we have a 7 kilogram mass stretching a spring that is 6.6 meters. What do we know? We need to find the spring constant. If it asks you to find the spring constant, you are looking for a force, aren't you? Because F equals negative kx. So let's draw a picture here really quickly. We've got this thing that is stretched out and hanging. So it is stretched some distance from what would normally be equilibrium. So it is stretched downwards. So 0.60 would be our change in x value. Okay, so that's our x. Now, what are the forces? Well, let's talk about that. We have, from here, we've got a force downwards, which is the force of gravity, correct? Well, what do we have upwards? Well, this thing has a restoring force, a spring force that's trying to return it to equilibrium, which is up. So, the spring force in this case is equal to gravity. Okay? Now, be careful. It's equal to negative gravity, isn't it? The negative of gravity? So plug that in. So if we plug this in here, we get what? So this would be negative mg. So negative mg, I'll go over here, has to be equal to negative kx. So the negatives go away. So we're left with a mass of 7, gravity's 10, k we don't know, and we know x is 0.6. So if we divide, we should get k is approximately 117. Now this would be force divided by distance. Force is newtons, distance is meters, so it's newtons per meter. That's the units for the spring constant. It says, now, what is the frequency with which the mass vibrates? So we know frequency is equal to 1 over the period. Well, we know the period is equal to 2 pi square root of m over k. So if we plug this in, we get 2 pi times the square root of the mass, which is 7.0 kilograms, divided by k, which is 117. We take and we multiply that out, we get about 0.65. And we know frequency, this is the period, this is seconds. I'm sorry, wait a minute. That was dumb. That is not 0.65. Let me figure that out. What is this? 2 pi. So I'm going to start with the inside. I'm going to take 7 and divide it by 117. I'm going to take the square root of that. And then I'm going to multiply it by 2 and by pi. And I get 1.53. So this is approximately 1.5369. Okay, and that's seconds. So that is the period. So now we know the frequency is equal to 1 over that. So if I take that and I get 0.65 approximately. And this is seconds, but this is seconds to the negative 1. So we call this 0.65 hertz. Okay? All right, so that's example B. Oops, sorry. There are only 2 types of positions that we're really interested in. So now let's look at example C here. We've got a spring with a spring constant, right? 40 newtons per meter attached to a surface, and a block is 0.25 kilograms. The block is brought into a position 20 centimeters from equilibrium. So this 20 centimeters from equilibrium, we know this is K, this is M, right? This is mass. So what we know is this is brought 20 centimeters from equilibrium. That means that is our delta X, isn't it? And released and allowed to oscillate. It says draw a free body diagram of the block when its position is negative 20 centimeters. So if it's negative 20, that means we are taking it and we are literally moving this thing out to here, aren't we? So we have stretched this thing out to there. So what is our free body diagram going to look like for that? Well, we have, of course, the force down. We have the normal force up. And then what do we have? Oops, I'm sorry. I just did, guys, I don't know what I'm thinking. Negative 20 centimeters is the other way, isn't it? It clearly shows that on our graph. Negative 20, so it's going to compress it. So if we're moving it to the right, which is what this means, this is to the right, then the spring force has to be which way? You got it. The restoring force of the spring has to be the opposite way, which would be to the left. Okay, this is determine the period. Well, period is T equals 2 pi square root of M over K. So we just plug all that in. 2 pi square root of M, 0.25. K is 40. And we get approximately 0.5 seconds. Determine the max speed of the block. Well, this is easy because it's going to do, we're going to use energy. So mechanical energy initial equals mechanical energy final. Well, when it's pushed in, it only has spring potential energy. And once it's finished, it just has, as it's moving, we've got maximum kinetic energy, don't we? So what that means is we are 1/2 kx squared equals 1/2 mv squared. Okay. The halves go away. That's nice. So we know that if we solve for v, we're going to divide both sides by m. It goes away and take the square root. Okay? So now, what is our max speed? Well, we can plug all this in, can't we? So let's plug in. We know that V is going to be equal to the square root of k, which was 40. Matched displacement is 0.2 because it's 20 centimeters. And we're going to divide that by the mass, which is 0.25. So we're going to get a velocity that is about 2.5 meters per second. Okay. Now it says derive an expression for the displacement of the block. Well, remember, the displacement of the block is going to be x of t equals a cosine omega t. Okay? We don't have to worry about phase shift at this point. We know what a is. A is the amplitude, which would be 0.2. And we know omega over here is going to be equal to what? Remember, we said that was 2 pi over the period. So 2 pi over the period, and we said the period was 0.5. So we end up with a period, or an omega of 4 pi, don't we? So this is 4 pi. So let's write it out. We know that x of t is equal to 0.2 cosine of 4 pi t. There we go. So now it says let's plot the displacement. Well, what do we know about the displacement here? We know this thing is going to start where? Well, it's going to start with some displacement, isn't it? At time 0, it's going to be displaced. Then it is going to move to equilibrium, which would be a displacement of 0. It is now going to go, and then, so this would be in the first chunk. The next chunk, there are usually 4 phases, aren't there? The second chunk, it's now opposite that. So if this is at x naught, this is at negative x naught, then it's going to go back to equilibrium, and then it's going to go back up here again, isn't it? So it's going to look like this, isn't it? Now, what do we know? Let's do, so this is displacement over time. This would be in meters, and this would be in seconds. So now we got to go to velocity. Well, we know the velocity starts at 0, and it is going to be accelerating and be at a maximum. We said, remember, we said it was at a maximum as it passed equilibrium, so it is going to go to some maximum here. And then as it gets to its max displacement in the other direction, it goes back to stop, doesn't it? Right? We better be careful, though. Let's think about this. It's starting to the right, didn't it? So its velocity was to the left, wasn't it? So we got to be careful about this. So it's actually speeding up the back way, and then it goes to here. And then on this next one, it would go to here. And then as it gets back to its max, it's 0 again. We know this thing is going like this. Now, let's talk about, so this is velocity, meters per second, over time. Now, you might be wondering, why am I drawing all these lines? Because I'm trying to make sure you understand that what that looks like at equal places in time, okay? So if the velocity is 0, we said that the, what? We said that the acceleration had to be at a maximum. So if it's moving to the right, the acceleration had to be to the left, which makes it negative. So it is at a maximum negative. That's where it starts. And then when it is at its farthest position, or when it's going through equilibrium, acceleration is now at 0 because it is going the fastest it's going, which means it is also 0 here. So if it comes back, can you guess what it's going to do? It's now moving, and it's slowing down here, which means that it would be a maximum in a negative way, so it's positive acceleration that way. And now it's back at 0, which means it is now going the other way. So this guy is going to go like this. This guy's going to look like, acceleration is going to look like the opposite of the displacement, isn't it? With the velocity changing in between. Now it says plot the potential and kinetic energy. Well, guys, we know this thing starts with potential energy, which then goes where? Let's think about it. Good. It's starting with potential energy. As it passes through equilibrium, it has no potential energy. Does it? That is correct. And then it goes what? Back to having potential energy, which is all going to be positive because it's x squared. And it goes to no potential energy, and then it goes back to potential energy. So it is going to do this wavering between having potential energy and having no potential energy, won't it? As it then goes towards zero again. Now, kinetic energy. Kinetic energy starts with zero because it's not moving. Then at equilibrium, it is at its highest because velocity is at its highest, and then it continues to go to zero, and then it goes back to its highest point, and then it goes back to zero, and then it goes back to its highest point. So it's swapping back and forth. So this is my kinetic energy, and this is my potential energy. All right? Now, what do we know about two springs if they're connected in parallel? If springs are connected in parallel, do you understand that the spring force would be the sum? Think about it. If one spring is strong, then two springs are twice as strong because it's pulling on both of them at the same time. It is making it more stiff. So this would be the K for in parallel would be K1 plus K sub 2 and so on. Okay? The equivalent K would be. All right, now, what happens? So we're saying they're in parallel. Now, K, if they're in series, so we'll call this P in series, then it actually makes them more stretchy. Okay, so you've got one that's stretchy, and then you've attached another one to the end. It's going to take longer to stretch it all the way out because one's going to have to stretch first, and then the other one will stretch. Okay, so in this case, it doesn't work that way. It works opposite of that. What we say for K sub s is that 1 over K sub s equals 1 over K sub 1 plus 1 over K sub 2. So it is becoming more stretchy, not less stretchy. All right. Each spring stretches a smaller amount for the same linear displacement. Okay. Both of them stretch the same amount with parallel springs, so it adds. Now, two identical springs. Let's look at this guy. Two identical springs are shown, so we know they are parallel. And it wants to know what's the force constant for the spring. Well, let's look. First thing we have to figure out is K equivalent for parallel. We know that's going to be K of the first one plus the K of the second one. Since they're identical, it's going to be 2K. It didn't tell us what K was, so we're going to leave it as 2K. Now we need to talk about what's the force of each force constant. So we're looking for K of each spring. So let's do a little free body diagram here. We have FW down, and we have the force of the spring going up, don't we? So the force of the spring is equal to the force weight. Well, what is the force of the spring? Force of the spring is going to be Kx, but in this case it's going to be 2Kx, because remember this has this in it, okay? And that's equal to mg. So if we divide both sides by 2x, right? Divide by 2x, divide by 2x, then we get K. So we know K is equal to mg over 2x, which is going to be the mass was 5, g's 10, and twice the stretch, which is in centimeters, so that is 0.1 meters. Got to put it in meters. So 50 divided by 0.2 is going to give us a spring constant of 250 Newton meter per spring. Now, example F. We have a disc with a mass M, a radius R, and it has a rotational inertia. You know what? We are going to come back to this because we have not talked about inertia yet. So we are going to look at this later. So you can stop here. You don't have to do any of the rotational inertia stuff yet because boom, we're here. All right. Hope you've enjoyed this. I hope you understand it. We'll talk about some demo stuff and look at that spring, 2 springs versus in parallel versus in series next time.